Okay, so let's begin. So last time we finished this evaluation of expression using a stack, and then we started Q. So so stack has only a front or the top. There is no other access place, while Q has both front and rear. So new elements are enqueued in the rear, and the old elements are dequeued at the front. Okay, so this is first in, first out. So mathematical modeling is you can do is check whether the Q is empty, look at the front of the Q value. You can also remove it, so that is called dequeue, and you can insert new elements at the rear, which is called nq, nqx comma q. Any questions? So in particular, now if you want to access AI, then which is I distance from the front, then you have to keep dequeuing I times. So let us implement this now using an array. So you can have some idea about what your Q will be at max, let's say n, right? So based on that, you can declare the array, and you can maintain two variables, front and rear. Will this be enough? Assume that Q is less than equal to n at all times. Still, this will not be a solution. Just declaring an array of size n will not be enough, right? Because when you dequeue, then the front will keep moving forward. So ultimately, the front will try to actually overstep this last cell. So you cannot just so just having information about n is not enough. So that is the question. So what to do when let's say this rear pointer goes to n from n minus 1. So at that point, there is a segmentation fault happening, or I mean, you haven't even created that cell in the memory, but you know that there are free cells in your array early on. Like 0th cell at that place is at that point of time is empty, and your array is already declared of size n. So how do you plan to reuse that? What should you do?
Reallocate the pointer to 0.
Yes, but how do you do this in a very simple step, in a very simple way? Yeah, so that is the mod arithmetic. So what you do at this point is loop around. So mathematically, this looping around expression is the following. So rear is rear plus 1. So your rear is moving forward. So at n minus 1, you will do plus 1, so it will become n, but there is no location n, so you should do mod n. Okay, so mod n will give you the remainder between 0 to n minus 1. So n mod n will become 0, right? So which is a declared memory location. So you can go there, and if you do rear plus 2, then that will become n plus 2, which will become 2. Is that right? n minus 1 plus 2. It will become n minus 1 plus 2, which is n plus 1, which is 1. So right, so the arithmetic will be correct. So this is the looping around, and then you can loop around infinitely many times. Right, so the queue has this structure that will allow you to just keep reusing the space as long as the data, the number of cells that the queue uses is at most n. Right, so that is the pseudocode. So rear has to be this, and front has to be. So when you dequeue, then the front also increments. Okay, so the first statement goes inside the NQ, and the second formula goes inside DQ. So this is the NQ, and this is the DQ. Sorry. Any questions here? So DQ will move the front, and NQ will move the rear in the same amount of space. Yeah, so that finishes the definition and implementation of queue. We'll see one interesting example in a pseudocode of how queue can be used cleverly. But before that, there are many interesting comparison questions about stack and queue. Okay, so they are somehow related, although not efficiently. So for example, can you implement a stack by a queue? Can you? Is it possible to implement stack using a queue? So using a queue means that somebody has already given you a pseudocode, somebody has already given a subroutine. You don't need to look inside the subroutine. Some implementation of queue is there, which means the mathematical models has been implemented. Just using those operations, now can you write a code for stack? So stack, let's call it stack S and Q. So using queue model that somebody else, your friend, has implemented, can you implement a stack S, which is push and pop?
When you can keep dequeuing elements up till the point.
Yeah, exactly. So that is the easy solution. That is the only solution, that the queue code which you have, without changing that code, you just use NQ DQ and implement push and pop. But what will be the time complexity of that? For size n, it will take time order n. Right, so it will take maximum time, because in the queue implementation, when you will ask for DQ, you will get something old, while in the stack implementation, when you pop, you want the most recent thing. So in the queue implementation, you have to call again and again DQ, so that you get to the most recent element, right? So there is no way to avoid this order n time. You have to.
So we have to use only one queue.
Yeah, there is only one queue implementation given.
Then the popped element where will be.
No. So when you DQ, you NQ it. So from the front, it goes to the rear. So this is again looping around, and the most recent thing will come at the front. That you can now say is pop. So you can do this formally at home. But this is very expensive, so it's of no use, but tells you still some kind of comparison between these two data structures. Can you implement queue using a stack? That's a harder one. So now somebody has given stack implementation, which is push and pop. You are not allowed to change that code, but you are allowed to call that code in your own code where you will implement a queue, which is DQ and queue.
Are we allowed to use two stacks?
No, this is just one stack.
You can't take elements out and put.
Exactly, yeah, so it seems impossible. But there is a cheat code for this. So you can read about the cheat code. So this can be done. Well, so simple answer here is actually no, but there is a cheat code which is that you can use recursion here. So on the stack code. Now this is a cheat code because when you write a recursive code, I have told you that the operating system will make its own stack. So now there will be two stacks. So there will be a stack S which your friend implemented, and there will be a stack, other stack, which the operating system will implement. So using the two stacks you can do queue also, but that's only a cheat code, this is not allowed. The correct answer there is actually no. So you should see this also as an exercise. Third is which can be done is implement queue using two stacks. Okay, this can be done, but this again will be, basically in the stack implementation, the given implementation, you will keep popping till you reach the base. But as you are popping out, this has to be stored somewhere. So in the second stack, you can push it. And this in the end will give you the DQ implementation. So it's very expensive. This is also order n time. Okay, so you have been given very brief hints. Expand on that as an exercise. If you just enter these questions in GPT or Bard, it will give you the pseudocode. So it will give you the C program. So you can have a look if you cannot solve it. But these things are tricky, especially question number 2. How do you do recursion here? This is a tricky code. So you can think about that. Now the more interesting thing, which is using queue in a real problem. So this problem is finding a path in a maze. Okay, so shortest path in a grid. So this is a grid, maze is a grid with obstacles. So what you have to do is you have to write a program where the input is a grid n cross n, and there are some accessible cells or empty cells, and there are cells which have obstacles. Right? So basically obstacles, you can think of it as a mine. So if you put your feet on the mine, then you will explode. Right? So you want to avoid those, and you want to go from cell S to cell T in the grid. So what is the shortest path? You want to find that. So write a program whose input is a grid So just a 2D array. So each value is Boolean, Gij. This is either 0 if it's an obstacle, so there is a set of obstacles. If Ij is one of the obstacles, then it is 0, and otherwise it's 1. And you are also given the distinguished cells S and T. So source and the target cells. So from S you want to go to T, avoiding the obstacles and using the neighbors. So from S you can go to one of the 4 neighbors in one step, and then from there you can go to their neighbors and so on. Avoid the obstacles, reach T. Or say that T is unreachable. Distance can also be infinite. So that's the output. From S to T, and the rule is that in one step move to a neighboring cell. Which is 1 out of 4. Right, so neighboring cells are in the 4 directions, and you can move in one step to one of those. Yeah, so basically the problem is defined. How fast do you think you can solve it? What is the algorithm for this? Can there be a linear time algorithm for this, order n time? There cannot be, right? Because maybe the obstacles are so adversarially placed that you will be forced to visit almost all the cells, also depending on S and T. So it can be order n square. So it really depends on the input. Right, so you cannot say that this will have a fast algorithm in general, but still, so Q cannot give you a miraculously fast algorithm, but it can give you a clean pseudocode. Okay, so this is what we'll use the Q for. Do you have any idea about a brute force solution? If you were forced to implement this, how will you implement this without Q?
Explore all possible outcomes, and whenever you come and cross an obstacle, you can just return back.
Yeah, but so that's a horrible algorithm. So that will be like going over all the subsets. So that will be 2 raised to n, 2 raised to n square, right? So that in practice will not work. If in your competitive programming you are given a 100 cross 100 grid, then 2 raised to 100 is just impossible. So that backtracking will not work. But there is a better algorithm, kind of brute force also. What you do is you just go from S to all the cells of distance 1, and then from there you go to all the cells of distance 2. Okay, so you basically, this is called a ripple. So you create a ripple from S, and then you explore all the area of the ripple. And that can be implemented by a for loop. So that should be the practical code. So let's give the brute force as well. Brute force is backtracking based. So this will be then exponential time. Or will not have a proper time complexity analysis. So a more clever algorithm is ripple based. So this iterative algorithm instead of backtracking. So here what you can do is create a ripple from S. And let the ripple move forward incrementally. So this ripple idea means that S is your center, say in water or in a lake, S is the center, and when you throw a stone at S, then the ripple is created which slowly grows. So it's ever expanding concentric circles, right? So the ripple expands, and what it does is that at distance d, it explores its neighboring atoms, and it goes there, right? So it goes from d to d plus 1, then from d plus 1 to d plus 2, and so on. So that is what you want to implement here in a pseudocode. So how will it look in this discrete situation? So this is the obstacle, suppose. And so you want to start from here, that's your S, and you want to end inside here, this is T. So the ripple will flow like this. So this will be the distance 1, this of course is the center, right? So the ripple, you create the ripple, which means that the cell having the cell S has label 0, distance 0. So this we can call D. This is the D function of the ripple. So that is 0, then its two neighbors will be 1, and then this will be 2, right? And so on. So this will, the ripple will take some time. Maybe I will not complete it. And so on. So as the ripple grows, you see that it is getting closer to T, right? And ultimately, so it avoids the obstacles. So the obstacles are not, I mean, they have d equal to infinity. So we will not be going there. We will not be exploring the neighbors of this obstacle, which is black. We will only be exploring the neighbors of non-obstacles, right? So that is why it forces you to go through a circuitous route. So you will come here, then you will come here, and then you will hit T. And then finally, this will be distance 6, I think, if there is no mistake. Okay, so this is the ripple-based idea, starting from S and then moving incrementally. Any questions here? Can you implement this in a C program? This physical ripple?
So we can use the keyword to do this.
Yeah. How?
We are on some given level. We will pop all the elements. We will put all the elements of the given level in a queue. We will pop all of those, and
You mean DQ and NQ? Yeah. Right. Yeah, so that is so the Q data structure appears here in a very natural way. Okay, and for that I just have to draw one picture to convince you. So what this ripple is doing, it gives layers L0, L1, L2. In this case, it goes up to L6, which is the till you reach T. Okay, so these are the layers. So layer L0 has obviously only one cell. L1, L2 has many cells. So think of these as lists. So these are the distinct lists which are being created as the ripple moves forward. So in a naive implementation, you would have stored L0, L1, L2 as different arrays. Okay, these are different lists. So you might create different arrays for this to keep track of this, which will be very expensive. You have to create multiple arrays and so on, keep track of those indices. A much cleaner implementation will be provided by Q, because you know that you can do the following in a queue. Use a queue to store this and go from Li to Li plus 1. So all you have to understand is this. So the queue has this as front. This as rear. So I mean it's a long queue, but let us only focus on Li and Li plus 1. So where do you think Li is and Li plus 1 is? Front or rear? So Li plus 1 has to come towards at the back of Li. Okay, so because Li is the old thing and Li plus 1 is the new thing. So what this picture is showing is that first you inserted all the elements of Li, which are basically cells that are at distance I in the ripple from S, and then so you basically enqueued Li one by one, you dequeued, and when you dequeued, then its neighbors you enqueued. So when you dequeue and you enqueue its neighbors, then you are enqueuing Li plus 1. Okay, so Li plus 1 comes towards the rear side. So this is what has happened. So dequeue Li and enqueue. So okay, I should say some element, you will get some element, right? So let's say cell, what am I using? C maybe. So C in Li. So dequeue C, cell C from Li, and then enqueue the neighbors, the neighborhood of C in Q. Okay, so C is, for example, your cell at distance 1. So there are two cells. So both of them were first enqueued, and then when you will dequeue, you will get one of those cells. Look at its neighbor B and enqueue that. Again dequeue another cell, so you will get the second cell at distance 1. Look at its neighbors and enqueue them. Okay, so Li, so as you are dequeuing, Li gets removed, Li plus 1 is inserted, and so on. Is this clear? This is how your pseudocode will do the modeling of the queue. And the pseudocode actually can be written here. It's not, so now this becomes very easy. So distance on a given grid between S and T with obstacles. So first you set each cell distance you set to infinity. Create empty queue. So the cell S, that distance is obviously 0, and you can enqueue it. Okay, so now the queue is alive with one cell. So when you will dequeue it, you should look at the neighbors and enqueue all of them. That will kickstart your loop. So the loop is the following: while not is empty queue, you dequeue, get C, and go over all the neighbors. What do you do with the obstacles? So you skip the obstacles. So go over all the neighbors of C which are not obstacles. Okay, so B is a neighbor of C which you have just dequeued. If it is not an obstacle, then you do the following. So when you have dequeued C and B is a neighbor non-obstacle, what do you know about the distance of B? Right, so that is the update. So whenever you enqueue something, you know the distance already. So when you dequeue, you know the distance. When you go to look at its neighbor, you also know its distance as +1. So you do this +1. So dB now falls from infinity to dC +1. So now it is accessible and you know the distance. And since you know the distance, you enqueue it. Okay, so that's it. So here you can finish while, and that finishes the function. Is this clear? So, I mean, if you want, you can return the distance of t basically here. So at this point, once the queue is empty, In fact, I did not even stop at T here, so this will just fill the distances of all the cells in the grid. And once that is done, you just stop and you return the distance that you were interested in. Okay, so this finds grid distance of every cell in the grid. Is this clear? So it's a very simple code for something which would be very complicated if you actually use backtracking and recursion and all that. It would be a horrible code and a horrible speed. While this is very clean. Once you have a queue implementation. So what is the invariant? In every code, this is what you have to prove, that there is an invariant that you are maintaining. So what is the invariant here for the correctness proof? So for every visited cell C, which means it was present in the queue at some point of time, the value of D at C is equal to the shortest distance from S. Okay, so this is what you have to prove. This in the base case, so you prove this by induction because it's again a ripple based idea. So ripple started at the center, so then the distance of S was correct, it was 0. And you can prove by induction now that at every point of time in this while loop, this is true. Okay, so by induction you can prove this invariant. That's essentially the main thing you have to do in the proof. So induction on distance. Use that. And what is the time taken by this algorithm? So time taken is essentially the area of the ripple. Okay, so if you reached T and you stopped, then the time complexity of this pseudocode is the number of cells that the ripple has seen. Okay, so the area of the ripple is the time taken. Any questions? Shouldn't we use what?
2 queues instead of 1 queue because the while loop, when you enqueue an element in the queue, your while loop will never end. It will never be empty.
Sorry, the value will never, no, but you are dequeuing.
Yes, sir, but simultaneously you are also adding some elements.
Yeah, so, no, so sure, so whatever you are saying is a misunderstanding you have to handle in the proof. That's the part of the proof. In the proof, you have to show that a cell which was dequeued is never enqueued.
No, I'm not saying that. I'm saying that when you dequeue a cell,
Yeah,
you are also enqueuing the elements corresponding to that cell.
sure.
So your queue never becomes empty. So
No, so you are not listening. If you show that once a cell is dequeued, that particular cell is never enqueued. So the total number of cells are only n square. So the queue will only have distinct cells across its lifetime. So it can never have more than n square cells. So this pseudocode will stop in n square time. So that will be the time when the queue will be empty. Uh, starts to, yeah, so that is true only in the very last fag end of the pseudocode. In the middle, you cannot say anything because the grid has obstacles. So the obstacles are arbitrary. So the length of the queue will constantly fluctuate. It's only before the end that it will fall.
But as long as it keeps not encountering the obstacles, its length will increase. The ripple goes on increasing, but then it fades away.
No. The ripple goes on increasing in the physical interpretation, but you have to see in the grid whether it is actually increasing. Is it that the number of cells from when you go from Li to Li plus 1, have they increased? Maybe they did not increase because the obstacles were very bad. So you are thinking of a calm lake. So there the ripple is concentric circles, but suppose your lake is very disturbed and there are obstacles, then it's a random motion.
Even then, the size will either stay constant.
No. You cannot say anything. It depends on how the obstacles are placed. So that is another exercise. Prove that you are wrong. But this was a good question that why did the queue become empty? And that point has to be added somewhere. Let's add it here maybe. That the queue becomes empty. Or cell is visited only once. So obviously, if a cell was enqueued again and again, enqueued, dequeued, then it will be an infinite loop. So that doesn't happen because the distance is growing, monotonically increasing. So that also you have to prove, and then it's actually part of this induction on distance. So when you work it out, you will see this. Any other question?
So wouldn't there be a stopping criteria in the while loop? Like once we have encountered our final.
Yeah. So that you can add.
Because like that reduces the number of iterations.
Yeah. You can add that. But since t is arbitrary, I did not add it. You can as well fill the distance of all the cells. Okay. Any other questions? So this finishes our discussion about Q. We'll move back to BSTs after this. Okay. So then let us go back to BST. Because there we have some very complicated things to cover before the midsem. So let's go back to balanced binary search trees. And now the hardness that we have to cover is in the balanced part. You have already seen one notion of balance. You have seen how it affects insert and delete. But we haven't seen pseudocodes for insert and delete that preserve that property. So this is what we'll now achieve. So what we want is, at all times height of the tree log of the size. Okay, so at all times, which means you do search, insert, delete, this invariant should be maintained. Height should be only logarithmic in the number of nodes in the tree. Okay, so how do you achieve this? So there are actually many solutions for this since the 1960s. The two most famous ones are So the two most famous data structures are named data structures. So first is AVL tree. So this is named after Adelson, Welsky, Landis. Okay, so this was the first self-balancing tree, which means that as you are inserting or deleting, there will be, so I hinted about, I even sketched how you can rotate a subtree. So using rotation, AVL tree actually self-adjusts, self-balances itself. And it achieves the invariant, the inequality that we want. So this AVL tree is one. You basically have to just implement what I said. Maintain the difference of height to be at most 1, and if it is being destroyed by insert, then you rotate. So if you just implement the rotation idea, you will get AVL tree. We will not do this, we will do something more complicated, which is called red-black tree. So this is by Dweibus and Sedgwick. So the first one was given by the Soviets, and the second one was given by the Americans. We'll go with the Americans. There is another reason why we'll go with the Americans, because this red-black tree is much faster in practice. I mean, both of them will ensure the inequality, but when you do many operations, then this cumulatively red-black tree will be better. Okay, so it has some cumulative advantages. And one thing is that it will seem as if in red-black tree the insert delete on average will be constant time. Okay, so instead of order log n, it will be order 1. Again, this is not true, but if you do hundreds or thousands of insert delete, then on average it will seem constant time. Okay, so this is why we'll go with the red-black tree, but this will need more notation, which probably we'll do next in the next class. Because they are much faster. On average, on insert delete. In search, you cannot have an improvement, because in search, if your average height is log n, then you have to search in the worst case log n. So that you cannot make faster, but in insert delete, in AVL tree, you might have to rotate many times, while in red-black tree, the rotations may be just, let's say, 2 times. Okay, so it's the rotation part which is much faster in red-black tree. So which is why we'll cover this. It takes a lot of time to even define this tree, but let's start. So the red-black tree has the following, it's a BST, which means that the nodes will follow the axioms of left being less than equal to and right being greater than. Is a BST such that, so there are 4 properties which we will do next time.